Hi guys, welcome to our first mini lesson on exponential growth and decay. What I'm doing in this lesson in this whole unit is I'm going to break these down one video per concept. And so they should hopefully be very quick videos for you. They're not going to be like the long ones we were doing before. So one thing that's going to help is you need to try to be as engaged as you can on your own. So in other words, if I say something like, hey, pause the video here and write down what you think, you really ought to do that because that's going to give you an opportunity to really put your own mental effort into it as well. I'm going to go through it and explain everything, but I think it's helpful for you to think of things on your own first. So what I want you to do first of all is hopefully you've looked at this PDF and maybe you've printed it out, maybe you haven't. I want you to look it over. And I want you to consider some of the questions here. And in fact, it will be really great is if you would write down what you think as answers for each of these. So again, I do want you to pause the video here. Think about each of these. Do you know what each of these phrases mean? And can you give an example? So take a minute, like I said, pause it here and see what you come up with. Okay, hopefully you have written down some answers now. I'm going to go through and talk through some definitions as well, and hopefully distinguish for you the difference between exponential and linear. So linear growth is when something goes up by the same amount every time. So for example, I have $50 in my bank account, I'm saving $5 per week. So it's going to go up 50, 55, 60, 65, and so forth. That is linear growth. Now, when we talk about linear decay, it's very similar. It's just that something's going down by the same amount every time. Okay, an example, I have 50 M&Ms in front of me and I'm eating one every minute. That would take a lot of self-control to only eat one M&M per minute, but that's what I'm talking about here. So you have 50, it goes down to 49, it goes down to 48, it goes down to 47, etc., and you're just eating one per minute. All right, the difference between linear and exponential then is when we get to exponential, we're talking about it's going up by the same percent every time. Not the same amount every time, but the same percent every time. So, for example, you've probably studied in your science classes cell division. You start off with one cell, that splits up into two, and then those split, and you have four, and those split, and now you have eight, and so forth and so on. That is exponential growth. It's something that's growing not by the same amount, but by the same percent every time. You're multiplying by something rather than on the first two, we were adding something. And again, a similar deal for decay. Exponential decay is when something goes down by the same percent every time. So if you start off with a car, let's say it's worth $20,000, it's going to lose 10% of its value each year. And so it's not losing like $500 each year or $2,000 each year, it's losing a percent, 10% of the value each year. So those are some examples. I do want to take a second over on the margin. You don't have to write all these down that I'm showing over here, but I want to show you the tables of what those instances would look like. And I guess before we get to that, we can talk about number 5. Number 5 is that the difference is linear changes by the same amount every time, but exponential changes by the same percent every time. And so, like I said, the tables, I kind of went over some of these verbally, but numbers 1 and 2, those were linear. It's going up by 5 every time. Number 2, it's linear. It's going down by 1 every time. Okay, but number 3, this is when we were talking about like with cell division. With cell division, you're going to multiply times 2, multiply times 2, multiply times 2. So rather than adding every time, like we did up above, we're going to multiply every time. And on number 3, we were multiplying by a whole number, times 2, times 2, times 2. It's not always a whole number. In fact, usually it's just a percent, not a whole number. And so we see an example of that on number 4. And number 4, if the car starts off at $20,000 and it's losing 10%, well, 10% of 20,000 is 2,000, so we would subtract 2,000. 10% of 18,000 is 1,800, so we would subtract that. 10% of 16,200 is 1,620, we would subtract that, and so forth and so on. So rather than subtracting the same amount every time, we're subtracting a different amount. But another way to say that is we are actually multiplying by a different number each time. What I should say is we're multiplying by the same number each time, because if I take this and I multiply it by 90%, that would be 0.90, then I would get 18,000. And if I take that and multiply that by 0.90, then I would get 16,200. If I take that and multiply by 0.90, then I would get 14,580, and so forth. So every time, instead of adding a certain number, I'm multiplying by a certain number. That's the difference. Let's look at what it would look like graphically. So when we talk about linear, we're talking about our good old friend slope-intercept form. So linear growth means that you start somewhere, you have some starting amount, a bank account, how many M&Ms you have, whatever, and it is growing from there. And it is going up at a constant rate. It has that slope. And mine's not a perfectly straight line, but it's going to go up and over, up and over, up and over, etc. That's how much you're gaining every time. And that should be a straight line. Linear decay is, again, it is a slope-intercept form. It's just it has a negative slope. Okay, I have 50 M&Ms, and I'm eating an M&M every minute. I'm losing 1 M&M per minute. So my graph is going to look like this. It's going down. And again, that rate is the same between each one. Just how much it's losing. We're just subtracting a number every time. How about some examples? I'm curious what you could come up with for examples. I'm not sure if you filled those in before. So if you didn't, take a few minutes right now to fill in these 4 examples here of what would you say would be an example of linear growth, an example of linear decay, an example of exponential growth, and an exponential decay example. Pause it here and write at least one example down, if not 2. Okay, I am curious what your examples were. So maybe in our chat, we can talk about what some of your examples are. But in that one example, a delivery company charges $1 per mile. The cost goes up the farther away they have to drive. Or a plant grows 1 centimeter per week. As time goes on, the height increases. Both of those would match with a graph similar to this. Or linear decay. You're paying off a debt at $20 per week. As night falls, the temperature goes down 1 degree per hour. And you're paying a constant amount. You're paying off $20 per week, so it's a constant rate of decay. And as night falls, the temperature goes down 1 degree per hour. Again, we don't know what the temperature was to start, but it's going down 1 degree every hour, so it's the same amount every time. Okay, exponential growth, though, it has a different shape. Do you know what that shape is? If you think you know what that shape is, take a second to draw that on your graph. Okay, mine is certainly not perfect, especially on the left here, but it will hit the the y-axis. And that's like, usually that's going to be our starting point, but it could come back before that as well. So it is going to hit there, and it goes up a little bit, 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 and then it just keeps getting more and more and more. And so it actually, in the beginning, let's compare it to the ones up above. In the beginning, it might actually grow slower than these two. Well, let's compare it to this one especially. It might go up slower than it does, but then it's going to reach a point where it crosses over. I'm going to draw that on here so we can kind of see what might happen. It might go up a little bit slower, but then once it takes off, it really takes off and starts going really, really fast. And that is what makes exponential growth so powerful. It can really take off and grow really fast. In the beginning, it's really slow. But then you hit this point where it just, boom, it just really takes off. And so examples, cell division. The zombie population during the zombie apocalypse. That was kind of a random example, but kind of big into movies and some of the literature right now. Or a viral social media post. Same thing, like someone posts something on Instagram, and then a couple people like it, and then those people see it, and then their friends see it, and then their friends see it, and so forth. And that's how it goes viral, is that a few people more, and then their friends and their friends and their friends, and so forth. I have a little GIF that I might try to post. I'll try to find that GIF that shows that pretty well. Okay, exponential decay, similar deal. Exponential decay will have a starting point. You've got a lot of something, and then what happens over time is it decreases over time, but it just gets smaller and smaller and smaller. So, for instance, radioactive decay. Have you ever heard of half-life? I'm going to put this up here because sometimes it does go that way. Half-life. So you cut it in half, cut it in half, cut it in half, cut it in half, cut it, and you just keep cutting it in half. That would be an example. Another example is a drink cooling down. That actually is an exponential example, not a linear example. When drinks, hot liquids cool down, they cool down in an exponential manner like this. So that would be another example of exponential decay. And so again, just to emphasize, you're not going the same degrees every time in temperature. You're going the same percent every time in temperature. And different liquids will have different percentages, but that's how it would work. Okay, that is the end of this video for today. Try to do some of the problems that are posted on the document on Google Classroom and see what you can do with those.